Hello, this is Jack Jackson. In this video, we're going to talk about a technique of integration called trigonometric substitution. So this is a more advanced form of substitution than we've done before, and it's useful when we have something of the form u squared plus a squared, u squared minus a squared, or a squared minus u squared in the integram, perhaps under a square root. And these, a is a constant and u is some function of x. So in this technique, what we do is we draw a right triangle and label the sides so that they have the proper Pythagorean relationship among the sides, so that whichever one of these you have is going to be one of the sides. We let theta be one of the acute angles, and this allows us to turn certain algebraic functions into trigonometric functions of theta. And then we proceed using the techniques from the previous section, where we use certain trig identities and so forth to do further substitutions. Sometimes we can use the algebraic technique of completing the square to get a quadratic factor into this form u squared plus or minus a squared. We'll cover that in a later video, and that will allow us to apply the trigonometric substitution. In this video, we're going to look at some basic examples here, three or four basic examples here. So the key is these to use one of these triangles here, okay? And first determine what the hypotenuse is. So if you've got u squared plus a squared, again, it might be under a square root. What you want to do is since this is a plus, then you're going to make it the hypotenuse if the sides are a and u. So notice that by the Pythagorean theorem, the hypotenuse squared gets rid of the square root, and that's u squared plus a squared, and that's this side square plus this leg square. So that's a Pythagorean theorem, and where theta is this angle down here. Now, since we have this, we don't really have a choice of where to put the square root of u squared plus a squared. We could possibly set this up with u as the horizontal side, or the constant on the vertical side, or the horizontal side. When you're given a choice, you're going to let the u be the vertical side. In other words, the variable expression, maybe it's just x, or maybe it's some expression of x, like 3x or something. You let that be the vertical side, and the a, some constant, 4, 6, whatever, it's going to be down here on this side. So let it put the constant on the bottom and the variable on the vertical side when you can. Now, if you have u squared minus a squared, then the u, the one that's the positive term here, has to be the hypotenuse. And then the square root of this is going to be one of the legs. A is going to be one of the legs. Remember, we said if we have a constant a, when we have a choice, we're going to put it down here on the bottom. So we put the a here on the adjacent side to the theta, and then the square root of the u squared minus a squared is the other leg. Now check it out, the Pythagorean theorem still works. If you take a squared here, and then add to it the square of this, well, the square cancels the square root, so you've got a squared plus u squared minus a squared is u squared, which is the square of the hypotenuse. So the Pythagorean theorem works out correctly. Similarly, if you have a squared minus u squared, the one that's the positive is going to tell you what has to go on the hypotenuse. So a is got to go there. We'll take the a to be the positive number there, the positive square root of whatever that term is. So for example, if a squared is 9, we put a 3 here. Then whatever the base is here for u, that's going to be your variable expression. That's going to go on the vertical side. Remember, we said use u on the vertical side when it's not the hypotenuse. Use a on the horizontal side when it's not the hypotenuse. And then the hypotenuse then, according to the Pythagorean theorem, is the square root of this a squared minus u squared. Again, check it out. If you square this, you get a squared minus u squared. Add that to the square of this, u squared. It makes the u squares cancel. We get a squared, which is the square of the hypotenuse. Now, from this triangle, you can figure everything out you need to know. Okay? You don't have to really memorize anymore. You just need to remember how this triangle is set up. But you definitely want to draw this. This is going to be a major part of what we're doing. So we make substitutions. For example, u over a, in this first example, is the tangent of theta. That allows us to solve that expression for x, because x is going to be inside of the u here, without dealing with this square root going on, right? So u over a is tangent of theta, so u is a tangent of theta. If we need to go further, we solve for x, but we have to find out what dx is in terms of theta as well, right? Dx is in terms of a function of theta times d theta. And we can solve for theta if we need it to be the arctangent of u over a. And then the square root, use it with the constant side. That square root over this a is the, let's see, that's hypotenuse over adjacent side, so that is the secant of theta, the reciprocal cosine. And so that square root expression is a secant theta. If you don't have the square root, you just have this, then of course u squared plus a squared is a squared secant square theta. In a similar manner, you do all these others. And so when you're done with these, you'll end up doing these substitutions. Don't forget to take care of the dx when you're doing that. And when you do that, you're going to get a function of trig functions of theta. So let's look at some examples. You see this in work here. So here we see an x squared plus 4 to the fifth. Now, you always just try a straight substitution first. Your first instinct should be right away to try to let u be x squared plus 4. Then du would be 2x dx. Well, there's no problem with the 2 and the dx, but there's no x up here. So there's either no x or the wrong power of x up there. And so, in this case, it's not there at all. So a regular substitution is not going to work. Then the next step is this indicates that a trig substitution might be in order. And it was this first case of the triangle right there. So we see both terms are positive, so that entire square root is going to have to be the hypotenuse there. So the u is just x, right here, that's the vertical side. The a is the square root of the 4, which is 2. So notice x squared plus 2 squared is x squared plus 4. Square root of that is going to be the hypotenuse. And then with theta being down here. So that's your basic setup. So x over 2 is the tangent of theta, opposite over adjacent there. Solving for x is 2 tangent of theta. So if we have an x in here, we could substitute 2 tan theta in place of it. We also need that to find dx. So dx, okay, if this is x, dx is the derivative of this with respect to theta times d theta. So 2 is still along for the ride. The derivative of tangent theta is secant square theta, and then we have our d theta. Now what about the square root? Well, that's the hypotenuse here. If you take that hypotenuse over 2, you have the secant of that angle theta, so just solving for the square root. The square root of x squared plus 4 is 2 times the secant of theta. All right, so now let's come over here and start working with the integral, and this will sort of tell us what to substitute. First of all, that 5 is sort of in our way, so we just bring it out front. Now look what we have. The 1 over the square root, okay, is going to be, well, it's 1 over, and the square root here in the denominator can be replaced by 2 secant theta right there. And the dx, the entire thing has to be replaced by 2 secant square theta d theta. So see what I mean by making sure you take care of the theta, the d theta as well, and the dx, get that relationship to see what function has to come in here with the d theta to be part of the dx. That has to go in there. Now we simplify a little bit. The 2's cancel, one of the secants cancel. So it's 5 times the integral of secant theta d theta. Back before in Calculus 1 and in my review notes, we have where we can prove that this is something that is harder to work out, but it's one of the ones I told you to memorize. The antiderivative of secant theta is the log of the absolute value of secant of theta plus tangent of theta. And of course now we have a constant here. I'm going to call it C1 because I'm going to modify it here in a bit. All right, so so we have that. So if you take the derivative of the natural logarithm of the absolute value of secant of theta plus tangent of theta, then you'll see that you get secant theta. If you've never done that before, you should do that yourself once to just verify that that formula is correct. So now we have to substitute back. Well, again, the triangle is the key to substituting back. So just looking at the picture here, the secant of theta is going to be hypotenuse over adjacent. So it's the square root of x squared plus 4 over the 2. So that's where the secant of theta goes. It goes there. The tangent of theta is opposite over adjacent, so that's x over 2. Let me do a slight change here. What I meant to show here is that we have a common denominator of 2 here, so we can add the numerators. Square root of x squared plus 4 and then plus x. Now, one of the things that we have with properties of logarithms, when we have log of a quotient, it's the log of the top minus the log of the bottom. So it's the log of the absolute value of square root of x squared plus 4 plus x minus the log of absolute value of 2. Well, absolute value of 2 is just 2. But now, if we distribute the 5, we get 5 times this first logarithm. 5 times negative log 2 is a constant. We add that to an arbitrary constant, we get another arbitrary constant, so I'm going to call that just c. And so I'm going to leave that as my final reduced version. So it is, so that's what I got. And then when I ran it through the calculator, this is a TI Inspire down here, CAS version. It gave this to me without the absolute value. I think the absolute value is actually needed there. Or is it? Let me think about this just a minute. The square root of x squared plus 4 is always going to be, the absolute value of that's actually always going to be bigger than x. So when I add x, it's always going to be bigger than the absolute value of x. So when I add x to it, even if x is negative, you're going to get a positive number out of that. So yes, we can drop the absolute value here. You have to think about that though. It's a little bit tricky there to be sure that you can drop that absolute value. Okay, so we can get rid of the absolute value there. I checked it with the absolute value in. That's all right. It's still correct with it in there. It's just maybe a little simpler without it. So anyway, I checked it with a there's a TI Inspire, but here's a TI 84 check. I put the answer in here, which I put that version right there in. That y2 be the numerical derivative of y1 with respect to x, evaluated of arbitrary x, that's math 8, fill in the blanks like this. And then y3 is the original integrand, 5 over the square root of x squared plus 4. And if this is done correctly, the tables for y2 and y3 should match, or at least approximately match. And we see that they do match, in fact. So that is, in fact, a correct answer, and it checks out. All right, let's try another one. All right, you might want to see if you can try this one yourself. Okay, the integral of 2x squared over x squared plus 9 squared dx. Try it yourself. Press pause, come back when you have a solution. Okay, let's take a look. Well, it's a very similar setup on the triangle. These are both positive. So that's going to be the hypotenuse. The square root of x squared plus 9 is the hypotenuse. So then the square root of the 9 is the a, or the horizontal piece, and the square root of the x squared is the x there is here. So, all right, so we have that set up. Okay, and from that, what do we get? Well, let's see. We get x over 3 is the tangent of theta. So x is 3 tangent of theta. If I need it, which I actually do need it later on, theta theta is the arctangent of the x over 3. Okay, and dx from this top line is 3 times derivative of tangent theta, which is secant square theta, excuse me, times d theta. And then we might want to know what the square root is to do some substitution. That square root over 3 is the secant of that theta. So the square root of x squared plus 9 is 3 secant of theta. Now, we didn't have it with the square root. We had x squared plus 9 squared. So to get from the square root of x squared plus 9 square root to x squared plus 9 to the second power, you actually raise this to the fourth power. You square it once and it gets rid of the square root, and then you square it again to get this square. So we need to raise the right side to the fourth power. 3 to the fourth is 81, and we have a secant to the fourth. So that binomial squared can be replaced by 81 times secant to the fourth of theta, which is our new denominator over here. We have 2, and we need to have x squared. Well, there's x is 3 tangent of theta, so you square that. See, 3 squared is 9, and we have a tangent square theta. And don't forget the dx. 3 secant square theta d theta replaces the dx. So this last part in parentheses is the dx. This numerator, or this in this parentheses, it happens when you take this x and square it. And we already saw that the denominator is here. All right, so let's clean up a little bit. 9 times 3 reduces this 81 down to 3 in the denominator, and we left with that 2 in the numerator. So I bring that out front. We got our tangent square here, and we cancel the secant squares. We get a secant square left in the denominator. Now, there might be other ways to do this, but I'm going to just switch everything to sines and cosines. So tangent square of theta, tan of theta is sine theta over cosine theta, and since we square it, that's sine square of theta over cosine square of theta. Secant of theta is 1 over cosine theta, so secant square theta is 1 over cosine square. If you multiply top and bottom by cosine square theta, those cancel out, and you're just left with sine square theta. We should remember how to do that. You use the power reducing identity. It's 1/2 times, well, the 1/2 times can be brought up front. Half of 2/3 is 1/3. What's it 1/2 times? Well, it's 1/2 times 1 minus cosine of 2 theta, right here. So that's how the power reducing identity works. It also bumps the angle up to twice as much. So we have the integral of 1 d theta, which is just theta. And then we have minus the integral of cosine 2 theta d theta, which we can introduce a 2 and a 1/2, brings a 1/2 out front, and it's like cosine w dw, so you get sine of w. Last integral sign is gone, so we put our plus c. Now, we need to figure out what sine of 2 theta is in terms of x. Well, the problem is we have our triangle here set up only with theta, not with 2 theta. So we have to apply some trig identities to change this cosine 2 theta back into some trig functions of just theta alone. Then we can change it back to x's. So sine of 2 theta is 2 sine theta cosine theta. So sine theta cosine theta, the 2 times the 1/2 gives us a 1 there. Actually negative because of the subtraction there. All right, now we can substitute back in. As we saw before, theta is the arctangent of x over 3. So that's what theta is. Sine theta is opposite over hypotenuse. We'll come back here. And so that is x over the square root of x squared plus 9. And the cosine theta is adjacent over hypotenuse, so that's 3 over x squared, square root of x squared plus 9. 3 times, well, you have two fractions multiplied together, multiply the tops, multiply the bottoms. So when you multiply the numerators, 3 times x is 3x. Multiply the denominators, you get x squared plus 9. It's the same thing. That cancels the square root, basically. And I'm going to distribute the 1/3, so I have 1/3 arctangent of x over 3 minus, when I distribute the 1/3 here, the 3 cancels, I get x over x squared plus 9. And then, of course, we have our plus c. So there's our final answer. If we look at the TI Inspire, That's exactly what it gave us. This is arctangent. Another way to say it is inverse tangent of x over 3, and it's dividing by 3. That's the first term. Minus x over x squared plus 9. They never put the plus c. You have to remember to do that yourself. And here's the check in the TI-84. Of course, as always, pause the video, rewind if you need to see that any of those steps a little bit slower. Okay, so here's another one. See if you can try this one yourself. The family of antiderivatives of x cubed times the square root of 4x squared minus 25 dx. Work this out yourself. Come back and check your work when you're finished. Press pause now. All right, well, the first thing we should always try is just see if we can let u be what's under the square root. The problem with that is we do a derivative of the inside, you're going to get 8x dx. Now you got the 1x here, but then you've got to figure out what x squared is. That may be a little bit more problematic. Actually, in this case, I think we could probably make that work that way. Let's try it. But let's try it with a trig substitution for practice, doing it that way. All right, so this time notice that the 4x squared is the positive term here. So the square root of that, 2x, has got to be the hypotenuse. The 5, which is the square root of 25, is the constant. We're going to put that on the bottom. And then by the Pythagorean theorem, the other side is the square root of the 2x squared minus the 5 squared, or in other words, the square root of 4x squared minus 25 that we had at the beginning. So let's see, this time we want to think of 2x over 5 is the secant of theta. So x is 5/2 secant theta. So then we find dx. dx is 5/2. The derivative of secant theta is secant theta tangent theta, and then we have our d theta. The square root over 5 is the tangent of theta. So the square root there of 4x squared minus 25 is 5 tangent of theta. Now here's our original integral. Let's just substitute in. X cubed becomes 5/2 secant of theta cubed. The square root of 4x squared minus 25 is 5 tangent of theta. And du is 5/2 secant theta tangent theta d theta. So let's see what we've got here. We got 3 5s multiplied together, and another 5, and another 5. That's 5 to the 5th power, which is 3,125. In the bottom we have 2 to the 3rd, that's 8, times another 2 is 16. 2 to the 4th, in other words, in the bottom, the denominator. That's a constant. I brought that out front of the integral sign. Count the secants. There's 4 of those, so we have secant to the 4th. They're all multiplied. Tangent of theta times another tangent theta is tangent square. All right, now if you remember techniques from last unit, if they're both even powers, we wanted to have a secant square as being part of the du if we let the u be tangent theta. I've already talked about u up here, so I want to call it w this time. Okay. And so w is tangent theta, dw is secant square theta d theta. Secant square of theta is tangent square of theta plus 1, which is w squared plus 1. Okay, and then we substitute that in. Let's see what we've got. Let's see, we split off one of the secant square of theta out of this, d theta, to become the dw. That left 2 more secants here, so a secant square here, which was w squared plus 1. And this tangent of theta is w, so this is w squared for that term. Distributing, we get w to the 4th plus w squared. Okay, now we got a fairly easy step next. It's just a polynomial, so add 1 to the power here and divide by the new power. So this is 1/5 w 5th, and similarly 1/3 w 3rd. Our integral sign's gone, so we have our plus c. I'm going to factor out a 1/3 and 1/5. The 1/5 is going to cancel that down by dividing by 5 to 625. and the 3 times the 16 is 48. And I'm going to distribute a 3 and a 5. The 5 cancels here, leaving a 3, and the 3 cancels here, leaving the 5. I'm also going to factor out a w cubed, leaving a w squared here and no w's there. Substituting back in, w is tangent of theta, so this is tangent cubed of theta, then times 3 tangent square of theta, then we get plus 5, then plus c out here. 625 is out here, over 48. Now, got to substitute back in again. So we did, remember we changed x's to thetas and then to w's, did an antiderivative, went back to thetas, now back to x's. So these problems get a little bit involved. There's several steps to them. So looking back at our triangle, that's going to be our key here. We've got a tangent theta. We've got to figure out what it is. Tangent theta is the square root of 4x squared minus 25 over 5. Opposite over adjacent there. So we've got that here to the third power, and there it is to the second power. Let me do the one to the second power first on the inside. When we work on this on the inside, the square root goes away. And so we have 4x squared minus 25. The 5 in the bottom becomes a 25 in the denominator, so we have 3/25 in front of that. Still plus 5. This we have a 5 to the third in the denominator, which can cancel 3 of the 5's out of this guy here, leaving just 5 to the first power, and then we're still over 48. Now, 2 of these powers are going to get rid of the square root, leaving a 4x squared minus 25, and then the last one is just going to leave the square root of 4x squared minus 25. I'm going to factor a 1 over 25 out of this thing here, which is going to go here. One of the 5's is going to cancel, leaving a 1 on the top, and 5 times 48 is 240. Canceling out, so I'm going to distribute the 25 in here. Cancels the 25, leaves the 3 times this, which I'm going to distribute and get 12x squared minus 75. But the 25 has to be multiplied by the 5, so that's 125 there. Combine like terms here, we get 50. Okay, I'm going to factor a 2 out of this, leaving a 6x squared plus 25, which I wrote up towards the beginning. The 2 multiplies this, cancels the 240 down to 120. And so here's my final answer. 120th times 6x squared plus 25 times 4x squared minus 25 times the square root of 4x squared minus 25 plus c. And I do believe there's a way to do this with a simpler way, probably with the straight substitution, but this does show you a good practice of how to use this technique. So I'll challenge you to see if you can figure out how to do this with a more simple substitution, and then see if you get the same answer. But in any event, it does seem to check out. They wrote these two terms together as 4x squared minus 25 to the 3 halves. There's our 6x squared plus 25, and there's our over 120 there. So they have the same answer on the TI Inspire, and it does check out as well on the TI-84 using that check. All right, how about another one? How about a definite integral this time? The integral from 0 to 3/5 of the square root of 9 minus 25x squared dx. See if you can do it yourself. Come back when you've worked out your answer. Press pause now. Well, this time notice that the 9 is the positive term. So that tells us that the square root of 9, which is 3, has to be the hypotenuse. The square root of the 25x squared, which is 5x, that's going to be, we put our variable on our vertical side when we can, and that leaves the square root of 9 minus 25x squared as the other side. So this time, if we do the two sides that don't have the square root, the trig function that's best to use there is sine. So sine of theta is opposite over hypotenuse. That's going to be 5x over 3. Solving for x is 3/5 sine of theta. That allows us to find dx, which is very important. dx is going to be the 3/5 times the derivative of sine theta, which is cosine theta, and then we have a d theta. The square root over the 3 is adjacent over hypotenuse, which is the cosine of theta. So the square root is just 3 cosine of theta. So the square root of 9 minus 25x squared is 3 cosine theta. Now we have enough to do our substitution. The square root is 3 cosine theta, and the dx was 3/5 cosine of theta. And I just put a bracket around the whole thing, and I'll evaluate from 0 to 3/5 at the end. So I may be doing some substitutions, but eventually I'm going to have to get it back to x's. I'd rather do it that way than try to figure out what the limits should be when we change it. So let's see. 3/5 times 3 is 9/5, which I can bring all the way out front of the whole thing here. Cosine theta times cosine theta is cosine square theta. Okay, when we have an even power of cosine, and that's all you have, use a power reducing identity. It's 1/2, 1 plus cosine of 2 theta. The 1/2 I pulled out front of the integral and out front of this bracket, times 9/5 makes it 9/10. Now we break this into two integrals. The integral of 1 d theta is just theta. The integral of cosine 2 theta 2 d theta is 1/2 sine of 2 theta. Here I've done another substitution. Say w equals 2 theta. dw is 2 d theta, so I insert a 2 and a 1/2. And I've got cosine w dw, the antiderivative is sine w. But I still have to have that 1/2. Check that by doing a derivative of this to make sure it works out. Now I'm still not in x's yet, so I got to keep going. Now I've got to go back up here. From here, sine of theta is 5x over 3, so theta is the arcsine of 5x over 3. So that's what I replaced theta with right here. Oh, wait a minute. Sine of 2 theta. Well, I don't have 2 theta in my triangle. I only have theta, so I need to switch back to thetas. Sine of 2 theta is 2 sine theta cosine theta. The 2 and the 1/2 cancel, so that leaves a sine theta cosine theta here. Sine theta is opposite over hypotenuse. That's 5x over 3. Cosine of theta is adjacent over hypotenuse, so it's the square root over the 3. The square root being the square root of 9 minus 25x squared, and of course that's over 3. Get a common denominator here of 9. And I'd like to get all my fractions out front, so I'm actually going to take that little 9 out front and distribute inside, leaving a 1/10 outside. Leaves a 9 on the arcsine, and the 9 will cancel both of those 3's, leaving us the 5x times the square root of 9 minus 25x squared. Now that we're in x's and we've kind of simplified as much as we can, we're going to insert the 0 and 3/5, put in the 3/5 minus, put in the 0. So here's that expression with the 3/5 in place of x. Here's the expression with the 0 in place of x. Going to subtract those, and at the end, we'll multiply by 1/10. All right, let's see what we got. 5 times 3/5 is 3, divided by 3 is 1, so here we have the arcsine of 1. 5's cancel here, leaving 3. Let's see. 5 squared is 25, cancels that 25, down to 1. 3 squared is 9. 9 minus 9 is 0. Square root of 0 is 0, and you multiply it by this, you get 0. On the last one, let's see, on this one here, 5 times 0 is 0, divided by 3 is 0. The arcsine of 0 is what we have there. Here we have a 0 right here. 5 times 0 times this is 0 for the last term. So the only two terms we have are 9 arcsine of 1 minus 9 arcsine of 0. The arcsine of 0, the angle whose sine is 0, that's within the range that we would need from negative pi over 2 to pi over 2 is 0. And the angle whose sine is 1 in that range is pi over 2. So the only thing left is this part here. When you group everything together, we've got a 9 times 1 times pi is 9 pi for the numerator. We got a 2 times 10 is 20 for the denominator. So the final answer is 9 pi over 20, or approximately 1.4137, etc. Here I did it on a TI Inspire, and sure enough, we got 9 pi over 20. exactly, and I did it approximately, say approximately do it, and we get the same decimal approximation. So that checks out. Okay, so that gives you some idea about some trig substitutions. In the next video, I am going to talk a little bit about how we can use completing the square to change something so that we can use a trig substitution. All right, see you next time.